at so far with regards to channel routing, there we had seen that we did not allow any cycles in the vertical constraint graph. Now, since we did not allow any cycles in the vertical constraint graph, obviously doglegging was not a mandatory issue. Of course, we had looked at one algorithm, the dogleg router, which can place doglegs, but not with an eye to tackling or handling cycles in VCG, but rather to minimize the number of tracks required to obtain a solution. So, today first we would be looking at an algorithm which can handle cycles in the VCG, in fact, which can handle any kind of arbitrary constraints. Now, it is called greedy channel router. Now, before going into the algorithm, let me first take a very simple example to illustrate the basic concept. So, let us take a very simple example where there is a cycle in the vertical constraint graph. So, as you can see, from net 1 to net 2 there is a vertical constraint edge. Similarly, from 2 to 1 there is an edge. Now, in this method what we do, we systematically proceed column wise and go on routing the nets one by one. Like from here we start like this, from here we start like this. Now, in this second column, since there is a constraint, we cannot connect both of them together. So, what we do, we connect one of them and from the other point and let this proceed to the right, and from the other point let another net proceed to the right. Now, when we arrive at the next column position, these two net segments which belong to the same net 2 will finally get merged. So, we will be getting a solution like this. Now, the greedy channel router which we would be discussing now proceeds in a manner similar to this. Well, this router is greedy in the sense that it takes only local decision, it does not look at the problem globally, unlike the other algorithms. If you look at the algorithms like the left edge algorithm, dogleg algorithm, and also Yoshimura and Ku net merge algorithms, there we had looked at the whole problem in its entirety. There we had talked about the horizontal constraint graph, we had talked about the vertical constraint graph, and then we had combined them to get some solution. But the algorithm we would be considering now, namely the greedy channel router, this will not be looking at the whole problem at a time. This is the main difference of the greedy channel router as compared to the algorithms that we have seen so far. See, the algorithms we have discussed so far, one characteristic was that, well, whatever way we represent the information in terms of some graph, the channels were routed one net at a time. This was the characteristic. But the order in which the nets are routed, there actually some way we are selecting that. So, the left edge algorithm we are selecting that by the x coordinate of the left edge and so on. And all these algorithms were based on the basic left edge algorithm or some kind of its variation. Dogleg, Yoshimura, Ku, all of them were finally using the left edge algorithm. So, one main characteristic of these algorithms were that one net was taken at a time, routed, and then the next net was taken. But in contrast, the greedy channel router that we will be considering now, This does not look at the problem globally, it looks at the local subproblem and makes some greedy, you can say, decisions so as to try and make an optimum you can say optimum decision at the current column position. So, this routes the channel column by column, not net by net. It routes multiple nets at the same time. It scans the channel column wise and starts routing the nets all together. For whichever nets are encountered at the columns, they are routed all together. Column by column, routed means not entirely, one is not connected to. So, each net advances one column at a time. Okay. Now, at each column position, we apply a sequence of greedy heuristics. Of course, these heuristics are based on experience, so they are also intelligent. The objective of this heuristic is that in the next column position, the number of tracks that are kept free, that is maximized. So, if you take some greedy decisions at the current column position, so that the number of free tracks in the next column position gets maximized, possibly you will be getting a good solution subsequently.
The number of tracks?
Objective is to maximize the number of tracks available in the next column. For example, we are currently working with 5 tracks, for example. In the present column position, say we have seen that 3 tracks are used up, 2 are occupied, but if we straight away extend them to the next track, it is possible that the next track will be saying that we require 2 more tracks. But using some heuristic, you try to push the tracks on one side with respect to the next terminal that is encountered. We will see the heuristics, so that the number of additional tracks that may be required subsequently may be reduced. But of course, these are greedy approaches. This is not necessarily always true, but for most of the cases this is true. And since we are not looking at the problem globally, well, you can handle any kind of constraints, even cycles in VCT. This is the first algorithm we are looking at, which can tackle cycles in the vertical constraint graph. But if you have cycles in the vertical constraint graph, you will require additional column positions to complete it, as we had seen an example in our last class, that if you have cyclic constraints, you need additional tracks with dogleg to complete it. So, either in the middle of the channel or at one end of the channel beyond the boundary. So, you may need additional columns to complete the routing if you have cycles in the VCG, right. Now, let us see that what kind of greedy heuristics are applied in the column positions, then we will be working out with an example, so that you will understand how it works. Well, some of the heuristics that are used are like this. Okay. The first one is, of course, it is not really heuristic, this is what I had said, that you place the segments column by column starting from the leftmost. This says that if you have a channel which, suppose in the first column position you have 1 and 2, in the second column position say you have 3, there is a no connection, here you have say 4 and you have 1. Then what it says that you proceed column by column. In the first step you start net 1, you start net 2. Then the second column you see that, well, you are starting a new net here 3. So, well, if you do not have space, you can make a jog out here, let 1 come here, or if you have a space, you can start 3 from here. This will see through example. Similarly, 2 will be extended. Here 4 will be continued, and this one net which was there, that will be connected here. So, So at each column position you are doing something. So first let us look at the heuristic, then we will just work out a complete example. You place the net segments column wise, not net wise, unlike the previous algorithms, starting from left. Connect any terminal to the trunk segment as they are encountered. This means, suppose you are extending column wise a net, say corresponding to net number 1. Suddenly in one column position you find that, well, you have a terminal corresponding to net number 1, then you straightaway connect it to it. Connect it provided there are no constraints or conflicts. Okay. Sometimes you may see that two segments for the same nets are proceeding from left to right. So at the first opportunity you collapse them, you connect them with a dog leg, merge them together. This says that in the channel, suppose there are two nets, means segments for the same net which are proceeding. Due to some conflict before, you were unable to connect them earlier. So at the first opportunity you connect them like this. This says that you collapse this split net using vertical segments. Try to reduce the distance between two tracks of the same net. There is some heuristic for that. I am not going into the absolute detail of this, but whenever you have two nets corresponding to the same track, try to bring them as close together as possible, because finally you will have to merge them with a vertical line, and longer that vertical line, more is the chance of conflict with other nets. So just you try to bring them as close together as possible. And the next heuristic says that say these two you have merged, fine, but you have another terminal for net 1 sometime later. So you have a choice, you can either proceed with the net from here or from here. So which track we will be using to extend net 1? This says you try to move the nets closer to the boundary which contains the next terminal. Since your next terminal is on the top of the boundary, you try to follow a track which is towards the top as far as possible. These are the heuristics you follow. And sometimes, well, you normally start with a given number of tracks, but sometimes you may see you may need additional tracks. You may add additional tracks if necessary. So if you can provide additional tracks, if you can provide additional columns at the end if required, then this algorithm can always find out a solution. It can always complete the route. Okay. So now let us take a comprehensive example and try to work out on this. I think the concepts will be clear. Let us take a channel routing problem like this, where we have taken 5 tracks to start with. In fact, this problem can be completed in 5 tracks: track 4, track 5, track 4 and track 5. Fine. So we start it column wise. So let us use 2 colors for the horizontal and vertical. Well, in the first column you have only net number 1. Well, I am not shown the zeros, the unnumbered terminals are the zeros or no connections. So in the first column you have only 1. So you use the first track to extend net number 1. Now you encounter the second column. Then the second column you see that a net number 2 is starting. So let 2 proceed like this. There is another consideration for net 1. Instead of proceeding it straight away like this, see, the first time you start a net, you normally try to start it from the nearest available track. Now, the next consideration is that the next terminal for net 1 is on the lower boundary, bottom boundary. So, instead of extending it out here, make a dog leg and bring it down here. So, what we are saying is that let net 1 come down to here. Okay. In the third column, in the top there is no connection, here there is a connection. So, 1 you connect it to the trunk segment for 1, this gets connected. Now, 1 is still not finished, there are some other terminals for 1 also. So, 1 you extend, well, this 2 you cannot make a jog because there will be a conflict, although the next terminal of 2 is on top, you cannot make a dog leg at this column itself because already the vertical segment for 1 has been connected. So, 2 you will have to extend further like this. Now, you come to column 4. Column 4 you have two terminals 3 and 3 right one top of the other, nothing else. So, you straight away connect this 3 to 3 by a vertical segment, and now these two you will have to extend, right. So, since I have already connected this, again there are constraint, you do not have any other choice other than to extend this like this. Now, you have a choice out here. See, this is the net for 2, the next terminal for net 2 is here, and this is the 1, and 1 is also top, but 1 is later. So, 2 comes first. So, 2 will be given priority. So, net number 2 will make a, okay, sorry, I missed one point. This 3, although you have connected, there is another 3 terminal on the right, and that is towards the top. So, you also start a segment from here like this. Okay. So, from here net number 2 you will bring closer to this 2 as far as possible. Now, since already this is occupied, you can bring it to the second track. So, net number 2 you can bring it up to the second track. Net number 3 you extend, this also you extend. Net number 1, okay, this also has a terminal on the top, this also you okay, this you cannot do a jog right now, you have already made it, you extend it right now like this. So, you have arrived at this column where net numbers 2, well, I am just writing down for convenience, this is net number 2, this is net number 1, and this is net number 3, these are still proceeding. So, at this column position you have a terminal 2, you connect it to this. There is a terminal on the right, this will be proceeding. 2 also has a terminal on the right. Yes.
So can you change the colors? They're same actually.
Okay, so this colors you are unable to see. Okay, fine. So, instead of this black, let me use red. Okay. So, now at this column position, see, this 3 is proceeding like this 2 will also proceed because 2 also has a connection down, but it cannot go down here, well it cannot well this 1 will take a jog, 1 has the next terminal here. So, this 1 will get a priority of, okay, let us take blue, going up like this. So, 1 will go up and this 2 will also continue because 2 has a terminal like this. So, in this way it will go on. So, in the next column position this will be extended simply, this will come here, this will come here, this will come here. So, now we have terminals 2 and 1. So, 2 cannot, this 1, suppose you connect 1 first, this 1 you connect to this. since you have connected 1, 2 cannot be connected to 2 in this column position. So, this net 2 will have to be extended further on the right, and this net also, which was supposed to be connected, you cannot connect here, you also extend it to the right. So, now in the next column position there are 2 split segments of the same nets which are proceeding. Okay, 4 I missed now. Okay, 4 will be proceeding like this. So, 4 will be proceeding. Now, here the next terminal of 4 is towards the top. So, this will make a jog like this. So, 4 will proceed like this. 2 and 3 also has a terminal on top, 3 will proceed like this. So, similarly, the next column 3 will proceed and a connection will be made. 2 also will proceed, 2 has a terminal on top, 2 will proceed. Net 4 will also proceed, and 2 you can split, you can merge the split nets here itself, there is no conflict. So, 2 and 2 gets connected here. So, in this way it will continue. So, 3, the next terminal of 3 is both on top and bottom, does not matter, you just let it continue. 2 also it is on top, so let 2 continue. So, now a new net of 5 starts, 4 also, 4 it is on the bottom, 5 will continue, and this 4 will also continue. 4 will go up. Okay. 4 will go up, right. 4 will go up like this. So, in this way it will go on again. So, 3 will again continue, 2 will continue, 4 will go up and get connected here. This is 5 will proceed and 5 will get connected here. In the next step, well, I think one thing I missed, I made a mistake here, this net 1 also should go on, because there is another 1 terminal here. So, this net 1 should be extended like this. So, anyway, so this is how we are doing it step by step, and I am showing you the final solution, you can just have a look at it. So, the final solution looks like this. So, the net 4 which I was saying, it cannot go up since net 1 is going along this track, this net 1 I did not show there. So, net 1 will finally reach here, and means you can do this completion. So, you see here that in this solution the way we have proceeded, there are dog legs, there are so many nets which are split across multiple tracks. In fact, in this example, of course, there are no cycles in the VCG, but there can be cycles in the VCG also, which can be taken care of also. But this greedy algorithm is a fairly powerful algorithm. You can use it to route even very difficult routing problems, which otherwise the other routers or algorithms is unable to complete it in efficient way, but greedy router works pretty well. So, there are some other routing algorithms also, I am not going into the details of those. There is another method which is also which is also being shown to work well, that is called hierarchical routing. It says instead of looking at the whole problem in its entirety, you try to divide it up into sub problems and try to solve the sub problems one at a time, some kind of a hierarchy. But I am not going into the detail of the algorithm. If you are interested, these algorithms are available in the textbooks. But in fact, the hierarchical method or algorithm also can handle cycles in the VCG. It can handle such problems in doclegs. Just to summarize, the different routing algorithms that we have looked at and this hierarchical which we have not looked at, but if you compare them, all these models are grid based. Well, I have not talked about any algorithm which are not grid based. In fact, we will see later the power and ground routing, they have some consideration regarding that, where the width of the nets may be different. But the Yoshimura-Ku algorithm has been modified, I am not again going into detail of that, so that you can have some kind of gridless routing, where you can have the wires from any positions, the widths can vary, there are some weights which are assigned to the graphs using that. So, all the models we have seen so far, they are grid based. Doglegs, the LEA does not use doglegs, but the other methods may have doglegs. Of course, the net merge in the version which we have looked at, this does not have doglegs, but you can extend it. There is an extension which we have not looked at, there you can have doglegs, because in the net merge we are assigning a full net to our track. Vertical constraints, the basic left edge algorithm does not have, but the modified version have, and all these methods can handle. But cycles in VCG, only the greedy and the hierarchical routers can handle, right. Okay. Now, in fact, dogleg, net merge, greedy, these are all good algorithms. It depends whether you have cyclic constraints in the VCG. If there are no cyclic constraints, you can use dogleg or net merge routers. If you have cyclic constraints, you can use greedy, or you can use hierarchical also. It depends on your problem. Now, these are all 2-layer channel routers which have been pretty well explored, and the algorithms are very efficient. But the scenario today is that for routing in VLSI chips, we typically today have more than 2 layers available. Well, of course, most of the channels can be routed efficiently on 2 layers, we do not need more than 2 layers. But since more than 2 layers are available, there are many algorithms which have been reported which consider more than 2 layers. In particular, some work has been done on 3-layer channel routing. 3-layer means you have 3 routing layers. For example, on one layer you do the vertical segments route, second layer horizontal, third layer vertical, or the other way around, VHV or HVH. Now, here we look at one such algorithm. There are actually several such approaches which have been proposed. The net merge channel router, the basic Yoshimura-Ku had been extended to 3 layers. But the algorithm that we will be looking at is that you start with a 2-layer solution, you try to map it to a 3-layer solution, HVH routing from HV solution. And there is another approach which says that you use both HVH and VHV. Here the idea is that you have the channel, you divide the channel into 2 regions, one on top, one on bottom. The top region of the channel, it uses HVH routing, the bottom region uses VHV routing, and there is one track in between which is used to connect between the top segment, top zone and the bottom zone. There is some work which have been reported on this also. It has been found that the number of tracks you require this is less as compared to the others in general. So, let us look at this second method to start with a 2-layer solution to arrive at a 3-layer solution. Okay. So, this method again is conceptually similar to the Yoshimura and Ku algorithm. Well, let us try to recall what the Yoshimura-Ku algorithm did. We have a number of nets. If 2 nets are not in constraint either horizontally or vertically, then we can assign them to the same track. So, Yoshimura and Ku merged a couple of such nets into a composite net. Now, a composite net was treated as a whole, it was assigned to the same track. Now, in this case you can go one step further. One step further means you can define something called supercomposite nets. Say a supercomposite net, say for example, may consist of 4 different nets N1, N2 and N3 and N4. Well, out of these N1 and N2 can be placed on track 1 of the first layer, N3 and N4 can be placed on track 1 of the say third layer. So, I am using the same track, but maybe across layers. So, when you say a composite net, they can be mapped into the same track in the same layer. Now, a supercomposite net can be mapped into same track in several layers. So, this is the basic idea. So, let us see. So, in this algorithm we start with a 2-layer routing solution. Starting from there, we try to systematically transform it into a 3-layer solution. Now, the 3-layer solution we look at is HVH, not VHV. We are assuming there are 2 horizontal layers and 1 vertical layer, so that the tracks can be placed on 2 layers. So, just what I had mentioned, in Yoshimura-Ku algorithm, nets are merged so as they can be treated as a composite net and assigned to a single track. But here the composite nets are further merged into supercomposite nets, and our objective here is not to minimize the composite nets, but rather to minimize the number of supercomposite nets. Okay, fine. So, just continuing with what I had said, that 2 composite nets in a supercomposite net, they can be assigned to different layers, but on the same track, just what I had said. They will be assigned to the same track, but on the 2 horizontal layers. Now, we use a data structure to keep track of these kind of constraints. There is something called a track ordering graph. See, we have a set of composite nets to start with. The track ordering graph has the vertices which represent the composite nets. So, the track ordering graph can be the output of the conventional Yoshimura-Ku algorithm. So, after we have done conventional net merging in 2-layer routing, we have got the composite nets. So, in the track ordering graph, the vertices will represent the composite nets. There will be directed edges between some of these vertices, which will represent some ordering restriction on these pairs of tracks. Now, there will be some restriction here, as we will see. The restriction will tell you that some of, say, if there is a h from say Vi to Vj, this will tell you that the composite net represented by Vi must be placed above the composite net corresponding to Vj. There are some vertical constraints which will require Vi to be placed above Vj. Okay. So, these edges in the track ordering graph will give you some idea regarding the ordering in which the tracks can be assigned. That is why it is called a track ordering graph. So, composite interval Ti must be routed above composite interval Tj if there exists any particular net Np belongs to Ti and Nq belongs to Tj such that in the original VCG there was an edge from NP to NQ. Because Ti is a composite net, it can consist of 3 nets. Tj is also a composite net, it can consist of 2 or 3 nets. Now, if any one net from Ti has a vertical constraint with any one net of Tj, then Ti has to be placed above Tj. Okay? This is the idea. So, now let us see with an example how this works. Well, here is a complete example which had been routed already using Oshimura and Ku algorithm. Well, here the font size is slightly small, but I am telling you, here you have a 5-track solution. On track number 1, you have nets 1, 3 and 4. Track number 2 has 2 and 5. Track number 3 has 1, only 1, net number 1. Track number 4 has, well, there is a dogleg here. Well, here we are considering a solution, a 2-layer solution. So, here track 1 is also placed on T4, track 1, track 4. Okay. So, this is a solution which uses dogleg. So, this is not necessarily the output of Oshimura Ku, it may be output of any algorithm, any routing algorithm. There are some doglegs here, so no problem. T5, the 5th one, 2, 4, this is again 2, 5, 2, 4, 5. Okay. Now, this is the track ordering graph where this represents track 1, track 2, track 3, track 4 and track 5. Now, we have seen these are the 5 nets. Now, with respect to the original problem, if you also show the VCG side by side, these are the 5 vertices 1, 2, 3, 4, 5. I am showing the vertical constraint graph. So, 2 on top of 4, so in H from 2 to 4, 1 on top of 2, 3 on top of 5, 4 on top of 5, 2 on top of 4 already there, 4 on top of 1. Okay. So, this was the original VCG. You see that in the VCG there is a cycle also, that is why we required dogleg to break the cycle. Well, now the point to note is that with respect to the VCG, if you inspect the VCG and this list, you can identify these edges. Say from track 1, which consists of nets 1, 3 and 4. Well, you look at the edges where it is going, 1, 3 and 4 edges are going, well, just other than 1, it is going to 2, 5. So, 2 and 5 correspond to nets T2 and T5. So, there will be an, sorry, 2 and 5. Okay, just you can inspect this solution and find out. You need not have to look at the VCG originally. See, from T1 there is a, this is your track 1. So, track 1 says, say for example, in first column position there is nothing, in the second column position there is no constraint as such. Well, there is net number 2 in the 5th track. So, there will be an edge from T1 to T5, then here first track out here, there is no constraint here, then first track next position is here, 4 out here, 4 is in track 4. So, there will be an edge to track 3, 2, 3, 4. Okay, so this is no constant, sorry, this is no constant here, constant is here. So, this must be placed above this is track 3. So, T1 to T3 is in it. So, T1 T5 and T1 T3 are the two edges corresponding to here and here. Similarly, you can look at the other nets and try to find out which net has to be placed above which. For example, from track 2 T2 there is one constraint here. T2 has to be placed above T3, this edge. Similarly, here T2 has to be placed above T5, this edge. Similarly, T2 to T4 there is a constraint here, T2 to T4. So, these three edges are there. So, in this way you can construct this track ordering graph. Track ordering graph will tell you that in which order or what is the relative ordering of the tracks which has to be placed above which. Well, if you are looking at an HVH routing problem, so you are trying to place or keep these tracks within two horizontal layers, but the composite net that you have already defined, that has already been mapped to one of the tracks out here. Well, you are not going to break that composite net anymore. You are trying to see whether two different composite nets can be placed on the same track on the two H layers out of these 5. For this, you can look at this graph. This graph is more like a precedence graph. If you treat these nodes as some jobs or processes to be executed and these arrows indicate the precedence constraints. So, from top to bottom as if we are considering the tracks. So, you see what are the things which can be done in parallel. Suppose we have two processors which correspond to the two horizontal layers. So, if they can be done in parallel, you put them on the same track on the two layers. So, one possible schedule from this graph can be obtained like this. In the first step, you can assign T1 and T2. T1 and T2 there is no edge between them. So, this can be assigned to the first track. Well, in terms of the processor scheduling analogy, we are considering it the first time unit. These are the two processors as if. This is an analogy you are taking. So, after these two are done, so these edges are also done with. So, now, well, T3, T4 are independent now. So, now you can take T3 and T4 together in the second step. In the last step, you are left with T5. So, starting from the track ordering graph, you can get a schedule like this. The schedule tells you that which are the tracks which can be put as a super composite net and assigned to the same track on the two layers. Now, once you have this schedule, you have several alternatives. So, now you know you will be requiring finally 3 tracks T1, T2 and T3. These are the super composite tracks. Now, the first track, well, if I represent them by lowercase T1 and T2, you can place T1 and T2. In the second track, you can place T3 and T4. In the third track, you can place T5. But now we have a choice. There are 2 layers one top of the other. So, either I can put T1 on top and T2 below, or T2 top, T1 below. There are 2 layers. Even on the same track, I can put this above this or this above this. And similarly, T5 other is empty. So, I can put T5 on top or on bottom. So, I construct another graph where you can say each level in the graph, these are the levels, okay, 1 level, 2 level, 3 level. These levels indicate these super composite tracks T1, T2, T3. based on these two possibilities, you have two vertices in each level of this graph. The top vertices says T1 is on top of T2, the second one says T2 is on top of T1. This says T3 is on top of T4, T4 on top of T3. Similarly, T5 null, null, T5. So, this graph captures all the possibilities you can have in placing these two tracks across the two layers. Now, once you have identified the vertices, you also connect them with edges across successive tracks. These edges will be having some weights. Well, of course, I am not showing you how the weights are coming, but weights are indicating that how many vias you require between the adjacent layers if we do the assignment like this. Say some of the edges are labeled as 2, some as 1, some as 3. 3 means you require 3 via connections if you follow this followed by this. At the beginning you add a dummy source node S and a dummy target node T, and you treat this problem as a minimum flow problem, and you find a path which will be minimizing the total weight. So, in this example, for instance, the minimum weight solution will be this. So, this says that in the first one you place T1 on top of T2. In the second one you place T4 on top of T3. In the third one you place T5 below, on top it is empty. So, if you assign the tracks in this way to the two layers, this graph helps in minimizing the number of via connections, because anyway any path you select, that will be one feasible solution with the same number of tracks, 3, but the via connections may vary. So, if you find a minimum cost path in this graph, that will give you a solution with minimum number of adjacent via connections. Okay. Fine. So, actually we have looked at a number of channel routing problems. In fact, one thing I will not go into the detail. I had mentioned that there is another kind of a problem called switchbox routing, where there is a routing region with terminals on all 4 sides. Well, I will not going into detail because there is no good and deterministic algorithm for switchbox routing. All the algorithms available are heuristic in nature, and there is no well defined layer as in channel routing, vertical, horizontal, nothing like that. The main objective of switch routing is somehow or the other you have to complete the routing. So, this is certainly much more difficult problem as compared to channel routing. Here the main objective is to ensure that all the nets are routed, because the channel size is fixed, your switchbox area is fixed, but there is no reserved layering. Horizontal, vertical layers you can put unconstrained anywhere you want. There are several algorithms which have been proposed, greedy approach, RIP. See, in fact, in switchbox router, in some cases when you are unable to find a path, you can use some version of the Lee's algorithm or line search algorithm also to find out a path. So, it is more like somehow or the other you try to find out the path. Okay. And even there is an interesting method also called Beaver, which is based on some concepts of computational geometry. These methods all work pretty well. So, I am showing you the solution of one reasonable size switch box. This is taken as example in many papers and many you can say benchmarks. Here you will see that there are some nets like this entire connection is put on the same track. Similarly, this on a different layer but on the same track, same means layer. So, there is no concept of separate horizontal and vertical layering here. So, although this is a 2-layer solution, but the nets can be laid out arbitrarily with any kind of horizontal and vertical segments on any layer. Okay. So, there is no better method available for switchbox routing as compared to this. So, to summarize, so we have seen that there are two kinds of problems, channels and switchboxes. Grid based model is the most popular, which we have seen so far. Layers to the different net segment, that is what we do, different net segments we are assigning to the different layers and tracks. So, main objective of the channel routing is to minimize the channel height, the total routing area, but for switchbox routing the main concern is routability, to complete the routing. Okay. So, in our next lecture we shall be starting our discussion on some specialized routing problems, like one is I told you clock and power routing, and second is that over the cell routing, where in addition to the channel we can route the cells over some other available areas. Okay, so this we shall be considering in our next class. Thank you.